Well, welcome back to the SEAM Studio, ladies and gentlemen. And this time around, I'm going to breach a topic which many people will not be used to, but I needed something just to define something like the constants that we are seeking while we are flying. So bear with me. I think this will be, it is just to make it a little bit easier. But let me give the definitions first. Flight constants. Those constants selected to ensure flight to specified perimeters. Ah, my goodness. Specified perimeters. So let's just get it right at there in the beginning. Height is always something that we either want to keep or we want to change it. Whoa, we're not talking about aerobatics, okay? We're talking about normal flying now. When we get to aerobatics, there are certain other rules. But when we are flying, we normally seek a height and attain a height, and then maintain a height. We normally select a speed that we want to fly up, or we put a certain power setting and the result is what it is. Such as, for instance, cruise power. If you put cruise power in straight and level, the speed you get is the speed you get. You don't control your cruise power. You put cruising power and the resultant, and those can change because of weight and density, altitude, and such a lot of stuff. I'm talking airspeed now, not ground speed. All right, speed. That's the one thing. And then heading. We're always asked to keep the heading a constant, or to change the heading as a constant. In other words, to use a constant bank. We don't fly around like that. So those are the basic constants that I'm talking about, and they determine the flight perimeters that we want to be. Right, we'll get into that. Flight perimeters, conventional flight is measured against predetermined perimeters, height, heading, and speed. Constants. Now, I just want to make sure that I've got, when I talk about constants, we're not talking about haphazard things happen. There is a constant, is a non-varying value, or I can talk about a constant that's got a constant or continual varying value. In other words, just to take the bank as an example, if we bank at 30 degrees bank, then that is a constant, and the rate of change is a constant. The rate of heading change is a constant. We're not putting that and then less and. So remember, we need to get a point of departure where we're talking about how do we control those perimeters that we are looking for in flying. Right, so here I've got, now at this stage I've only spoken about height, heading and speed. A little bit tongue-in-cheek, but remember that I know that we manipulate the power as well. Yes, I know you use the radios and stuff like that, and. But the things that will control the height, heading, and speed is through the controls of the aircraft, and you can say that the power is one of the controls. All right. So when I look at the perimeters, I will say there are either a selected constant or it must have a constant change. Or in certain stuff, it is just, in fact, a constant. Now, what I'm saying here is height is selected to be a constant. Let's say we're looking at, we want to maintain 7,000 feet. Then it is a constant. Then it is a constant. Then it's nothing further to do about it. However, let's say we want to establish a rate of climb or a rate of descent. Then there must be a change. I just used the sign delta there. But I say that the change must be a constant. We're either going to climb at 500 feet a minute or 800 feet a minute rate of descent, or whatever the selected must be. But that change, again, is not a faster and a slower and a faster and a slower. The rate of change of height, needs to be a constant. No, at will be a constant, not always a selected constant. If I want to change the height and I just simply push the nose forward and the speed increases, then the rate of change can be but what, anything. Or I will select that. Now normally, when we do a descent, we want to descend from a flight level to a position where we can start the approach at an airfield. And that descent must be planned very well. In other words, there's a distance, and it'll take us so much time to get there because of the ground speed. Therefore, to get rid of this, we'll have to descend at a certain rate. So those things are selected. Let's have a look at heading. Heading, if it's not a constant, the constant must be hang. So I want to maintain a heading of 180 degrees, then it is a selected constant. But I say to you, I want you to do a medium turn to the left. Let's say it's a 20-degree banking turn to the left through 360 degrees. It means that you must continue and maintain a steady bank of 20 degrees. In instrument flying later on, we're going to say, but we want you to do a certain rate of climb. And there are going to be rules of thumb on how to work out what must be the bank angle to give us the rate 1, the rate 2, or rate 3 turns. Okay? But that is coming in the future. For now, let's just concentrate and say that the flight perimeter heading is either a heading or a specific bank. Those two goes absolutely hand in hand. And then speed. I've just changed the sign because I had to say, hey, whoa. We don't want a constant change in speed. There will be a constant change in speed if we do, for instance, a loop. But we're not doing aerobatics. All right? So there's not a constant. From flying level and let's say having excess speed and then eventually settle on your speed in the climb, I know that there is a change of speed in the entry into the climb. I got it. This is not, though, the moment where I want to talk about this. We want to look at the steady climb speed. We want to look at the steady cruise speed. We want to look at the steady descent speed. We want to look at the steady approach speed, and so on. And when we make the changes, yes, there will be a change from, let's say the final speed is 90 knots and the VREF is 80 knots, then somewhere the speed is going to be bled down from 90 to 70 knots. Just an example. All right. But what I am saying is that speed is normally a constant selected or as a resultant. Why I say as a resultant? When I fly straight and level and I've put cruising power, let's say the cruising power in a Robinson 22 is 18 inches or 19 inches manifold air pressure. I put that. And the speed I get is the speed I get. All right? So that is a resultant. And that will stay a constant. If I don't make it heavier or lighter or anything, it'll stay a constant. Yes, I know on the long term you're going to burn fuel and blah, 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 and so on. But remember now, we're talking about the principle in the narrower sense. Sorry, in the wider sense. All right. When speed is selected, when do we select a speed? Well, when we join a circuit. We will say, all right, the downwind speed is this, the base leg speed is that, the final approach speed is that, and. So those are speeds that you are selecting, and you then change the power and everything to get the selected speed. All right. So there are no continual changes, so to speak. Power or thrust, again, power, I say again, is a resultant or a selected. And how can you say that? Well, I can fly straight and level and I can select either all the power, or I can select max continuous power, or I can select cruising power. So power is something that I can select. Or it can be the resultant. And by the resultant, I mean what is the energy output? I get into this aircraft, I pull all the power, I mean, it's going to give me X power. Maybe the one engine is not as fit as the other one, it'll get different results. But sometimes we use power. If the power is completely down, there will be a certain result. If the power is completely up, there's a certain result. So, yeah, if you power to select to have it full, it's that. But I wanted to say that the power available is not always a constant. But it is a result. It is there. It's not something that we determine in the air, it's already there on the ground. So just a little bit of recap there again on the power available and power required. Remember, this was the power required, and there we've got the power available at the top. And there is, remember now, the in-ground effect power required. This is what you require to stay in ground effect, and that is the power that you stay out of ground effect. But the top one is the power that you have available. So you have got all that way to play with it, and there you've just got less to play with it. All right. Power available, decrease means less power margin available. If my power available is less due to increase in height, you can see that the excess power and obviously the operating speeds and so on and height and everything changes with it all the time. 3 speeds, just wanted to recap that. The first speed here at the bottom is the so-called Vy, and for Vy we're going to need so much power. Have we got power? Yes, we've got so much power. This is all the excess power that we've got there. Or if we get to our lower speed that is formed by that tangential that we put there, we can say this is the endurance speed. And the endurance speed, you can see that there is less power available, speed is less, drag is less, and but on the total drag curve, obviously, it shows more. Then we have, when you draw this tangent in, you get your range speed, and that speed is roughly, remember we already talked about Vy times 1.32, and that speed is that speed, and you'll see we use that, and we've used it in the descending that we are saying. So we said that we climb and descend between these 2 ranges. That has been said in the previous presentation. Excess power above, excess power can now be exchanged for height or speed or whatever. Same story, we've seen that. When we look at the flight energies, and this is a concept that I need you just to, it's not a big deal to understand, but just to know that they are there. The first one is the mechanical energy, and the mechanical energy is simply thrust. Thrust is due to the engine. Yes, you can say to me, I can use potential energy to get that as well, but listen, I am now first dissecting the 3 different main energies that is coming to play. So hang in there. The next one is height. Height is then potential energy. So now we've got the mechanical energy, and we've got the height, we've got the potential energy. And then we've got kinetic energy, half rho v squared, which is the amount of forward speed that we've got. So there's one energy, there's one energy, and there is one energy. And those are the three energies. So now let's look from takeoff into the hover and forward flight. What are we doing with those energies, and how do we exchange those energies, and what happens to those energies? All right, so here engine started on the ground, idle, rotors engaged, engine now at flight idle, it's ready for takeoff. We've got the ground here at the bottom, and the wind is coming from the front, and we've got the three there. Now on the next slide, it doesn't go forward, I'm just showing that it is now moved into the hover. All right, that's all that I'm trying to say here. It's not moving forward. Increase in CP to get into the hover, into ground effect. How did we do that? By simply taking thrust and put that into height. We used the first amount of energy, mechanical energy, to get that little bit of potential energy, which in many cases in the hover could be 3 feet, 6 feet, 10 feet, 12 feet, whatever, depending on the size of the helicopter. Remember that in-ground effect is what we're talking about, also a safe height, so that if you get an engine cut in the hover, that you can survive the landing in a single engine, well, obviously in a multi-engine as well. Now, once we got in the hover, that was the first power exchange, was to get height, and that was the potential energy. And now we're going to take it at the same height, we're going to now use the excess power to start creating a little bit of speed there. Allowed forward motion through the cyclic movement forward, increase the CP slightly to go through transition. And now, once we have got the speed, we want to maintain the speed and we want to climb up. At 40 knots increase to climbing power, cyclic slightly rearwards to climb the helicopter. So at this stage, what we are doing with the energy exchanges, we are still maintaining a certain amount of thrust to maintain the speed, a constant. Oh, constant. Okay, sure. That was a bit ugly. But we want to keep velocity, okay, a constant. Okay, that is what we want to do. And then the excess power is put into height and into the climb. And then once we leveled off, now we do not want to climb. We have now already satisfied the height. We want to just fly straight and level. And now if there's any excess thrust left, and you put, let's call it normal cruising power, then the speed will increase and the energy now only goes, and that will go until the aircraft has reached its maximum cruising speed for the amount of energy available. But now it's level. It's already got its height. Okay. So that's just normal cruise. So energy usage, energy available are there to support the required perimeters. I'm bringing the two. So kinetic energy, speed will always be primary concern and is dependent on either power from the engine through the main rotor energy due to height gained, or potential energy. Potential energy is the height will always follow the satisfaction of the basic speed requirements. Because, okay, now you're going to say to me, yeah, but what if I climb vertically? Yes, you can. You can use all the excess power and don't have to put it into speed, and you can put it into height in the hover, in a vertical climb. No problem. You can do that. That's not how we normally use if we get airborne out of a confined area of stuff like that. But eventually we're moving from point A to point B. But yes, you could say that we can put it directly into potential energy. That's why it's called a helicopter. So the helicopter works inside the avoid curve, means zero or very low speed. Out of ground effect, however, means always more power. In of ground effect due to the changes in downwash, which affects lift and thrust. Mechanical energy, always be selected constant specific requirement, whether you want to climb, cruise or descent, circuit or landing preparation, approach, and so on and so forth, until finally when you're on the ground, you will select it 0. Now, let's go over to the selection of constants. In straight and level, and I need here more, not just the instructors, the newcomers to the game must look as well, but the instructors as well. Straight, oh goodness, sorry. Straight means to be able, straight and level. Straight means to give in a straight line. So the heading is a constant. And level means that height is a constant. And how will we know that the height remains a constant? By the way, just through the VSI indication, irrespective of the power output, but enough to maintain, select airspeed, blah, blah, blah. In the VFR flight, the attitude is selected outside with relation to the nose section of the helicopter and the horizon. Any change there will result in a height variation as well as a speed variation. Oh, a lot of things said here. Full power, cruise power will always give a resultant speed which is dependent on many factors, and so on and so forth. The point is that straight and level says, man, I want to maintain a certain heading and I want to maintain a certain height. That is straight and level, not climbing. All right? That's what it means. So those are the constants that we want to have. But if we climb, and I'm not taking zoom climb now into consideration, okay? It's a pre-selected speed we want to climb at. The speed will require a certain amount of energy to maintain, and the rate of climb is dependent on the excess power. Or you can say, look, I want to have a specific rate of climb. Note that during a climb, a difference in lift, usually less than that required to weight, is not that which provides rate of climb. It is the use of excess power that gives us the ability to climb. Okay. Climbing, again, just to continue there, only when the selected speed power requirement is applied, the rest can be converted, and we've said that now many times. The use of too much energy for the climb will result in an increased rate of climb and a decrease in speed. Rotation speed must be kept in mind. Oh, so why did I say that? I said, look, you can really take your helicopter and decide, I'm just going to do a vertical climb. Because I'm not going to climb at, let's say, 65 or 70. I'm just going to climb vertically. But remember, when you want to auto-rotate, you don't want to auto-rotate vertically down, you won't be able to use that as such because you will be in the void area, and this is where you will get recirculation and vortex ring or settling with power. So you actually would like forward speed. All right? So keep in mind the forward speed. If there's an engine cut, what is the minimum forward speed? Now I can tell you now that in auto rotations, your flare and flare effects are mostly the higher the speed until around about 40 knots, but from 40 knots below, very, very little help from that little friend. Okay, so keep that in mind. Descending during a descent, I say not taking a rapid descent into considering normal, there's a pre-selected speed. So we again are going to descend at a speed with rotation speed in mind. So if the rotation speed of this helicopter is 70 knots, then surely I'm going to try and say that my descent speed must be commensurate roundabout with 70 knots. Because I want to be able to go straight into and already have the kinetic energy that I require for the rotation. If you run out of power due to engine cut, the glide speed is due to an exchange of potential energy only, and there's a very, very specific speed that we're saying that this speed is now what we're going to use during the auto-rotation. No more power. So instead of the airflow coming from here, it's now auto-rotating and the airflow is coming from the bottom. And that airflow will help to maintain the rotor RPM. But that will be in the autorotative section. The selected and required speeds will require a certain amount of energy. Entire potential energy required to maintain is obtained from the energy locked up in height. Woo! Look at this. What I'm saying here, no height, no energy source. If there is no height and no energy source, then if you run out of height and you haven't got an engine, then you and Mother Earth are going to meet up. At what vertical rate, I don't know, and at what horizontal speed, I don't know. Vertical rate or speed, both of those can hurt. If you fall from 100 foot, there's a good chance that you can break and burst some internal organs as well. If you're going forward at 60 knots, 50 knots, and you hit a tree, well, that stop is going to be far too sudden for comfort. Right. So the use of more energy is required to manage the experience will result in an increase in speed and thus increased rate of descent, but it is a more rapid use of the energy source, depleting it, and it will happen quickly. So the quicker I fly, now in auto-rotation there's going to be speeds where we normally auto-rotate, but there's speed that we will auto-rotate a little bit faster. It will give us a little bit more translation lift and give us a little bit of distance. But the moment you've got over that speed, then all of a sudden the drag becomes the main factor. So don't think that everything can just happen in any direction without penalties being built in. Penalties are built in all the time. Note that during a descending, lift is less than weight. Mathematically, this will be explained during, and we have done so, and the rate of descent. Descending, what are the selections there in a descent? Well, we know that thrust and height as a combined is the source of energy. So we can use those two as rate of descent. So normally in descent, you will at a constant speed, you can have at least a constant rate of D if you want, and you can manipulate it by using the power. Remember, the speed when considering any usage must always be a constant. If speed is a constant and thrust is steadily increased, level flight, and. But remember, when we are selecting the constants of flight during a descent, what is it that we want? We want a rate of descent, we want a certain speed, and we want a direction. So again, those are the three things. How you use the energies to your backup, that's also slightly a different story. Descent can also be required rate with the power changes that we now know. Note that the delta in height is normally a constant, or the rate of descent. We descend 500 feet per minute for passenger sake and non-pressurized aircraft. The speed is, just keep that in mind, 500 feet for unpressurized air vehicles. The speed is normally also selected and not a random figure. But, you know, I was doing 80 knots right in level, and I've got 2,000 feet to lose. I can simply put the nose a little bit forward and start using as extra energy. I'll leave the energy where it is, but as extra energy, I'm going to start using up the height. That means that the speed will now increase to 100 knots. That's fine. If that is what you want to do, then it's predetermined and that's how you want to do it. Now, velocity not exceeded for the height on the little explanations where you are, or wherever it is inside your helicopter. Please have a look at that, because that becomes paramount, very important. An approach is also a descent, but now the aircraft Configuration has changed. And if you put undercarriage down, the drag is increased, and so forth. And you'll say to me, hey man, but I'm flying this Oak, it's got no wheels. All right, not all helicopters has got skids. Some of them has got actually wheels and something to retract, which will reduce the drag in forward flight. But once those wheels come out, then the drag will increase. When it's got done and welded like here, well, okay, there's going to be no drag change. Well, there shouldn't be any drag change. Most small helicopters do not have the retractable undercarriage, which leads to there's no configuration change. And that's normally why to get in and to land a helicopter that's already in this configuration, it's always in landing configuration. It's just a question of going in. But remember, there are certain procedures that one goes through. It is not something that is hard and difficult and makes a big change. But remember, you always go through it just to cover and make sure that you have covered all the points. Turning. During a turn, the lift vector is tilted vertical and orbital vertical component maintain level flight turn. The aircraft must be pitched up. Now here we've got the constants. It's a constant change of direction, constant bank. You can have a climbing turn or a descending turn or a level turn. All right, so now you must decide on the constants. The one thing is there's going to be a constant change of heading, whether we are climbing or descending. But it's a constant rate of climb or a constant rate of descent or a constant height. So those are the constants. So height will either be a constant or it will be a constant change. Heading will be a constant change. It'll go from a constant heading, constant change, unto a constant heading again. All right? And the speed, well, normally, in normal turns, there's going to be a little bit of a loss of speed. We don't do much about that. But remember, when you do steep turn and the speed reduces, it might actually mean that you'll have to increase the power, to climbing power, to maintain the speed. Always keeping auto rotation in mind. Now, oh goodness, how did I do that? Just want to make sure that we are there, right? Flying is not a random selection of any of the parameters. It is always selected. It is not a random selection. It is always selected. Height and heading during cruise. And it will end result in the speed being pretty much constant. Height, heading, and speed as constants in a circuit. Downwind is in a specific height, downwind is in a specific heading, and downwind is in a specific speed. So the approach. The changes of height climate is normally selected speed and at the rate of descent. Speeds will always be selected or as a resultant. The helicopter result required may be 0, which for the purpose of constants must always be considered a constant or selected. Height will always be selected, and when you want to attain that height in climb, the speed will be selected. The speed is a constant to get there, as well as your power setting. And that will result in a certain rate of climb. And then, if you want to change the rate of climb, that is fine. But the speed must stay a constant. If the speed stays a constant, then the resultant rate of climb during power manipulation is the correct one. If the speed starts changing, then it's not right. When the rate of change must be a constant and selected, the power must be adjusted. Attain this, always be selected speed, which is the primary constant. Selected speed, primary constant. The visual scan outside in reference to the horizon and point chosen with confirmation of inside indicators as exactly the basics for instrument flying. With a primary and secondary scan so designed to satisfy the selected parameters that needs to either maintain or attain. Wow! What am I saying here? That in normal flying, we know that I want to stay in level, I want to point outside, and I want the attitude, and I want to check it's clear outside, and inside the heading is a constant. All those are quite nice, but secondary scans, the balance right, yes, all of that, and that works very well. Should we go onto instrument flying, then instead of using the big horizon outside, instead of using the H, the horizon, we're going to use inside the AH, artificial horizon. Same thing, just miniature. Outside I can see attitude, I can see bank. Inside I can see attitude and I can see bank. So the one is just the God-given horizon on the outside, and the inside we've got the artificial one. Same function, except the outside one is for visual flight and the inside one is for instrument flight conditions. In conclusion, simply put, when you have no more source of energy through the power available due to engine cut, mechanical failure or fuel starvation, and you have run out of height, speed cannot be maintained anymore and the helicopter must be landed. Oh, it's one of those things. Speed needs something to feed it. Height, you can give it up. There's an energy that you can give into the system. Mechanical energy is there. If you take the mechanical energy away, then we are sitting only with two energies. That's potential energy and kinetic energy. Kinetic energy is what we must have. And the only energy to feed in to keep that, the only energy available is height. Nothing else. That's your potential. The helicopter can fly with as far as the basic speed requirements. So should be emergency main rotor RPM control in conjunction with the forward speed requirements to avoid very vertical descents must be considered. Yeah, the vertical descent is a bad one when you get close to the ground. Know how to utilize the energies at your disposal towards attaining basic kinetic energy requirements, the conversion of potential energy into rotor kinetic energy and kinetic energy, and finally the translation energy into the rotor system will be repeatedly demonstrated and taught during the landings. So, whoa, okay, this is a mouthful, and we're going now slightly from the theory to the practical, but I want you to see that the theory is 100% the basic, or the basic point of departure for the practical. It's not, okay, forget now what you've learned there, this is how we do it here. It doesn't work like that. If you do that, you're going to be bitten. Don't get bitten. It's not necessary. The conversions of energies, you must understand that. But I think you should after that. So, helicopter constants in flight, you can think for yourself that fixed-wing constants of flight are pretty much the same. They just don't have something like an auto-rotation, but they will also have a climb, a zoom climb, a descent, or you can go further in that. You can say we'll have a max rate descent. In helicopters, I could have gone to the advanced stages and say, hey, we want to really get out of the sky. How fast can you get out of the sky in a helicopter? Just collective down and auto rotation. No, there's methods that you can go faster out of the sky without hurting the machine or anything to that effect. But that is a topic for the advanced sections. In the meantime, keep the swattings. See you in the next round.